Today, the use of patch clamp is widely used in research to study ion channels activity. But what is an ion channel? What is the principle of patch clamp techniques, and for what purpose do we study calcium channels, and what are their implications in cellular physiology?
Ion channels are pore-forming membrane proteins that allow ions to pass through the channel pore. Their functions include establishing a resting potential, shaping action potential, and other electrical signals by guiding the flow ion across the cell membrane. Ion channels are present in the membranes of all excitable cells, but also on the membrane of other cells and eventually in the membrane of their organelles.
These channels can either be specific to one ion or be non-specific. All aqueous solutions are neutral, but the membrane of the cell acts as a capacitor, and an electromagnetic field exists on both sides of the membrane due to ions and charged molecules. As you can see here, on the inner part of the membrane there are a negative charge, and on the outer one there are positive charges. Ions flows are thus essential to modulate the resting potential of the cells, but they also have a role in the cell metabolism.
The patch clamp is a laboratory technique in electrophysiology which studies ionic currents of channels. It consists in an application of an electrode in a micropipette to a cell in different configurations. We can work in voltage clamp or current clamp. The current clamp technique records the membrane potential by injecting current onto the cell through the recording electrode. Unlike in the voltage clamp mode, where the membrane potential is held at a level determined by the experimenter. In current clamp mode, the membrane potential is free to vary, and the amplifier records whatever voltage the cell generates on its own or as a result of stimulation. A glass pipette containing electrolyte solution is tightly sealed onto the cell membrane and thus isolates a membrane patch electrically. Currents flowing through the channels in this patch ends flow to the pipette and can be recorded by an electrode that is connected to a highly sensitive differential amplifier. In the voltage clamp configuration, a current is injected into the cell via a negative feedback loop to compensate changes in membrane potential. Recording this current allows conclusions about the membrane conductance. A single channel recording is only a few picoamperes, whereas a global current can reach the nanoamperes.
During the cell-attached configuration, the recording pipette is sealed onto the cell. This configuration allows to control the patch membrane potential. Thanks to this conformation, the cell is not disrupted and its normal intracellular environment is maintained. But the exact value of the resting potential is unknown, and we need to measure it. This configuration measures microscopic current. To access to the whole cell, you must realize a section of electronic zapping from the cell-attached mode. So your cell is physically disrupted. We have an electrical access to the inside of the cell. But as the volume of the electrode is larger than the cell volume, soluble contents inside of the cell will go out and be replaced. Nevertheless, various compounds can be introduced to the cell interior. When using the inside-out configuration, we pass through the breaking of the cell membrane to remain with only a fragment of the membrane. The intracellular surface is exposed so we can play on the intracellular medium. When it comes to the outside-out mode, we start from the whole cell configuration. And when retracting the pipette, a fragment of the cell will reform itself in the pipette, giving us access to the outside of the cell. Those last two configurations make us able to study a limited number of channels.
Finally, we have to keep in mind that there are also intracellular ion channels. Indeed, 95% of the cell membrane belongs to intracellular organelles, as vesicles, endoplasmic reticulum, Golgi apparatus, and so forth. But organelles are into the cell, obviously, and too short and inaccessible to be monitored by patch clamp. Nevertheless, today we do have techniques to register intracellular channel activity. The protocol consists in lysing the cells in order to have fractioned membranes, isolating the different types of organelles by centrifugation, and then gathering the different membrane segments in a giant unilamellar vesicle. Then we apply classical patch clamp techniques on it.
We will now show you the patch clamp techniques in a real lab experiment in the Ficelle lab of Lille University with Antoine Faucheur. In the team lab, they use two cell lines that are prostate cancer cell lines from bone metastasis, C42 and PC3. Nevertheless, PC3 show a more aggressive phenotype with more metastasis. C42 only possess NIV sodium voltage dependent channels. PC3 have NIV and NILCN channels. They want to study NILCN channels in the PC3 lines. That's why they first study the NIV in the C42 line. The experiment is monitored in a Faraday cage to avoid electric noises. The micropipette is a glass capillary which is stretched by heat until the break, and then the type is polished by heat too. The capillary is filled with a solution that contains gramicinin, an antibiotic that will make pore in the plasma membrane, to work in perform patch clamp configuration. The gramicinin is only permeable to sodium, potassium, lithium, and cesium, so it allows a certain selectivity. A macromanipulator is used to seal the micropipette to a cell. They work in a voltage clamp at minus 40 mV and they study the ion flux. You can see on the screen at minus 100 mV there is an exit of sodium, whereas at plus 100 mV there is an entry of sodium. We know that sodium is involved because we can do an IV curve. Today the experiment doesn't work. Too many cells on the plate and the membrane resistance was too high.
NALCN are ubiquitous channels. They are involved in prostate cancer. They especially are essential in triggering action potential in neurons. So it will be useless to screen for inhibitors of NALCN. In these excitable cells, they are directly present on the plasma membrane, whereas in the prostate, NALCN are generally found in vesicle and then translocate to the plasma membrane. So it will be interesting to find a specific inhibitors of prostatic cargo involved in this translocation of NALCL channels. In this experiment, they use fetal veal serum as a non-specific agonist that activates this translocation. Here they are studying sodium channels, but with the same methods, you can study calcium channels. Besides, in this lab, they work both in sodic and calcium channel involved in the prostate cancer. Calcium channels are linked to many cellular processes. Calcium itself is a tertiary cell messenger, which is involved in many cellular signaling pathways and has a role in the cell homeostasis. We have different types of calcium channels, voltage-dependent and ligand-dependent ones. But there are also others, sensitive to heat, stretching, and so on, like TRP channels. They could be localized on the plasma membrane, like Aurélien, on the endoplasmic reticulum, like EP3R, and on the mitochondria, like VDEC. But there are also others, on lysosomes, peroxisomes, and so forth. To study calcium channels, the configuration cell attached is an important asset, as calcium channels are known to be regulated by intracellular second messenger systems, and this mechanism is not disruptive. What's more, calcium channels' activity can be studied. Perforated patch can be also useful because nystatin pores are permeable to monovalent ions but not divalent ones and second messengers. Furthermore, nystatin pores are impermeable to compounds weighing more than 200 Daltons. So thanks to the perforated patch, we can study calcium current that are lost rapidly in the wall cell configuration.
Some calcium channels, such as the inositol 3-phosphate receptor, and notably the IP3 receptor 2, can be studied thanks to the patch clamp techniques. This channel is mainly located in the endoplasmic reticulum. It's an intercellular calcium release channel regulated by the inositol 3-phosphate, the ITP, the calcium concentration, and different phospho and dephosphorylation chains. This channel is implicated in the circulatory cell system, in the heart function, and in the regulation of cell death and senescence.
Why are we studying calcium channels? Because calcium dysregulation is involved in so many pathologies. For instance, it can lead to an increase of proliferation, an aberrant differentiation, or apoptotic resistance. This leads to hyperplasticity in cancer tissues. Let's remember that cancer is both an augmentation of proliferation and a lack of apoptosis. Moreover, the role of calcium channels in the impairment of autophagy has been demonstrated in prostate cancer.